Hello, my name is Allison Surratt, and I'm presenting the work we have done so far on geochemical analysis of filtered tailings for the Cantong mine. Mining is a critical component of the move towards more sustainable living, but it can have significant impacts on people and the environment. To limit harm while meeting demand, updated mining practices are needed. Failures of conventional tailings storage facilities have also emphasized the need for safer tailings management strategies. And in 2020, the International Council on Mining and Metals created a new global standard for tailings management. This standard highlights the need for zero harm to people and the environment from mine waste management. Filtered tailings is a potential solution. However, there is still considerable uncertainty associated with the effects of storing potentially acid-generating tailings in a filtered tailings configuration. The Cantong mine offers a case study to investigate the behavior of PAG tailings stored in filtered stacks so that the environmental effects can be better understood. To start, I'll highlight the importance of critical metals, particularly tungsten, show you some information about the site, run through the basics of acid rock drainage and tailings management strategies, and demonstrate what filtered tailings are and why they're seen as an opportunity for the mining industry. Then I'll review my objectives for the project and discuss where I am with my current research and where I'm planning on going in the future. Critical metals are generally defined as commodities that are essential for economic security but have supply risks. Critical metals are also vital for sustainable development and therefore should be recovered in a way that doesn't negate the positive impacts their use can have. Tungsten is one of these critical metals and is important in many industrial applications because of its ability to maintain high strength at high temperatures. It is used in the mining, metalworks, and construction industries and does not have a reliable substitute. In 2018 and 2019, China dominated tungsten production, creating a supply risk for Canada and other countries. While Canada did not contribute to tungsten production over the past few years, Canada does have significant deposits. The focus of this work is on the Cantong mine, highlighted in red, but the Laned and Mactung mines are similar deposits located in the same region, so these sites could benefit from this research too. So now let's talk about the Cantong mine site. The Cantong mine is located in the Northwest Territories on the border with the Yukon. The site is within the Mackenzie Mountains and is on the edge of the Nahanni National Park. The Flat River, which flows through the site, connects to the Nahanni River within the park. Cantong is also within the traditional territory of the Dehcho First Nations. Cantong is within the Tombstone Tungsten Belt, where multiple deposits, including Mactung and Laned, have been discovered. The Cantong deposit was formed by a series of events including rifting, passive margin sedimentation, and orogenesis. The host rocks of tungsten mineralization were deposited in the Lower Cambrian to Middle Devonian. Tungsten mineralization occurred in the Cretaceous after the Columbian orogeny caused suites of felsic to intermediate plutons to be emplaced, resulting in metamorphism and skarnification. Cantong is a world-class tungsten-copper skarn deposit, with the tungsten suite Monzogranite pluton at the base, which has intruded the limestones, dolomites, and argillites. All skarn facies are mineralized with disseminated scheelite, but the biotite pyrrhotite and amphibole pyrrhotite facies have the highest grades. Ore-grade tungsten mineralization occurs in two ore zones, the open pit ore body and the E zone. Some of the minerals present include scheelite, pyrrhotite, chalcopyrite, carbonates, and silicates. So although this is a skarn deposit with carbonates, the ore mineral scheelite is associated with pyrrhotite, resulting in substantial amounts of sulfides in the tailings. The open pit ore body was officially discovered in 1959 and operations began in 1962. Production was very periodic from then until the site most recently went into care and maintenance in 2015. Early on, tailings were deposited directly on the floodplain of the Flat River, and you can see evidence of ARD in areas around the site because of this. There are currently 5 tailings ponds present holding about 6.5 million tons of tailings, the first of which was constructed in 1965. The tailings are classified as PAG because of the high amounts of pyrrhotite present, but the tailings in the tailings ponds don't show much evidence of ARD yet. Plans have been proposed to reprocess the tailings to recover more tungsten and convert the storage to filtered tailings facilities. Acid rock drainage refers to the acidic and potentially metal-rich waters that can result from the interaction of certain geologic materials with the atmosphere. Acid rock drainage is a major environmental problem associated with the mining industry. Abandoned mines in North America have left legacy problems of ARD with billions of dollars in cleanup costs and long-term environmental problems, showcasing the need for effective materials management in mining operations. ARD occurs when sulfide minerals are exposed to oxygen and water, and they react to produce cations, sulfate, and acid. For pyrrhotite, as shown here, oxidation by oxygen occurs when the minerals are in contact with the atmosphere. As that reaction occurs, ferrous iron is released into solution, and those ions can subsequently be oxidized to produce ferric iron. The ferric iron ions can then either react with water to form an iron oxyhydroxide, which can potentially sequester harmful metals, or the ferric iron can further oxidize pyrrhotite, resulting in substantial acid production. So the initial three reactants, the pyrrhotite, oxygen, and water, are the components that need to be managed. Common methods to mitigate ARD involve inhibiting the oxidation reactions from occurring, or allowing the reactions to occur, but then controlling the pH through buffering reactions. To stop the reactions from occurring, you have to limit the availability of some or all of the reactants, so either sulfides, water, or oxygen. Generally, limiting oxygen has been viewed as the most effective method, which can be done by covering the tailings. Conventional tailings dams use water to fully saturate the tailings and create a barrier, which substantially reduces the diffusion of oxygen. The second method uses carbonate buffering reactions to react with acid and is important for deposits that contain substantial amounts of carbonate minerals. However, the effectiveness of this method depends on the relative amounts of sulfides and carbonates and the volume of material. Using the data compiled by the World Information Service on Energy for major tailings dam failures, there have been on average 2 to 3 tailings dam failures per year since 2011. In the wake of the Mount Polley failure in 2014 and the Brumadinho failure in 2019, the industry has been under increasing pressure to find alternative tailings storage methods to reduce risk. There is this idea of the tailings continuum, which outlines different types of tailings storage methods based on solids content. As we move to the right from conventional tailings, we get drier and drier options. The focus of this work is all the way over to the right at filtered tailings. Filtered tailings go through a dewatering and filtration process to remove water so the final product has solids contents greater than 80% and usually aims for the water content to be close to optimum, in order for the maximum density to be achieved with compaction. Having tailings at their optimum water content means that the particles fit together in the densest arrangement without being too stiff, which is important for physical strength, but it also means that the tailings are unsaturated. Since the tailings must be unsaturated to achieve maximum geotechnical stability, the pore space is filled with both oxygen and water. As previously mentioned, those sulfides, oxygen, and water are the three components that can cause acidic drainage, so there is a major potential for geochemical instability in this configuration. Mineralogical changes can also influence stability because oxidation that results in acidic waters can cause changes in the stability of certain minerals, and secondary minerals that precipitate can have different strength properties and can change the amount of pore space present. With all of these connected pieces, there must be a balance between the geotechnical and the geochemical stability in order for filtered tailings to become an optimal solution. There are many advantages and disadvantages of the filtered tailings storage method, with the main advantage being the decreased risk of physical failure resulting in catastrophic flowing tailings. But other advantages include less space required compared to a dam, and the ability to recover water through filtration, which also reduces the amount of seepage. Progressive reclamation is also possible, which can allow the facility to be remediated to a stable landform. Disadvantages include higher operating costs and low capacities, as current filtration equipment can only filter relatively small amounts of tailings per day. Climatic conditions influence the stability, and as we've discussed, there's potential for acid rock drainage and metal leaching. So my main goal is to assess the viability of the filtered tailings storage method for PAG tailings from the geochemical perspective. With that, I have three main objectives. The first involves characterization of the samples to better understand the impacts each component might have. The second is to evaluate sulfide oxidation in a filtered tailings configuration over time and under different conditions. The third is to then assess the impact of that oxidation to see if there is potential for environmental harm or not. Currently, I've been working on the first two objectives, characterizing the samples and evaluating sulfide oxidation with samples at different water contents. The materials for this project were taken from Tailings Pond 3, or TP3, and 2 samples were taken over 2 years. Approximately 2 tons were taken in 2019, and approximately 120 kilograms were taken in 2020 at locations shown here on the map. The 2019 sample was air-dried and homogenized at CanMet Mining, and I received 2 30-kilogram buckets of this sample. The 2020 sample was taken by mine staff with a depth range of surface to 48 inches. This sample was shipped directly to Queens. Because the 2020 sample was separated by depth, I air-dried the sample for 24 hours and homogenized all 4 buckets using the sample splitter in the mining department at Queen's University. The methods used for the first 2 objectives of this project include geochemical analyses, mineralogy by SEM with automated mineralogy, and some synchrotron work. The standard Proctor test to determine the optimum water content, and column experiments, which are evaluated for water content by time domain reflectometry, sulfide oxidation by oxygen consumption tests, which use an electrochemical oxygen sensor, and pH and temperature using a soil pH probe. For the column experiments, column 1 was packed at the optimum water content, column 2 was 5% less, and column 3 was 5% more to achieve a range centered around the optimum. Once the tailings and water were mixed, they were packed to try to achieve a density of 95% of the Proctor maximum. Immediately after the columns were packed, the oxygen sensor cap was placed on the column for 24 hours to monitor the initial oxygen consumption. Oxygen consumption tests then occurred weekly, and outside of the 24-hour test period, the columns have been left open to the atmosphere. TDR probes were also placed in the middle of the column to monitor water content changes. Results as of November 2021 include geochemical analyses, mineralogical data, water content, and oxygen consumption trends. To start the characterization work, subsamples from the 2019 and 2020 samples were analyzed. Here the results are being compared to previous analyses conducted in different years to assess the heterogeneity of the Cantong tailings. This figure is showing the average element concentrations for various years, with the bubble size indicating how many samples were analyzed. In 2012, 152 samples were taken from multiple points within TP3 and were considered to be representative of the entire tailings pond composition. Samples taken and analyzed in 2018 aligned well with these 2012 results. Both Queen's and CanMet analyzed separate subsamples of the 2019 sample and obtained similar results, higher average iron, tungsten, and sulfur values than both the 2012 and 2018 campaigns. The 2020 sample also shows high iron and sulfur values, but average tungsten concentrations. Here is a breakdown of all the samples analyzed to show the range in concentrations. The 2019 sample is shown in the orange, yellow, and red points, with fusion values around 1 weight percent, while all other sample values range from approximately 0.1 to 0.6 weight percent. Since the 2019 sample has such high tungsten concentrations, it is likely that this sample was taken in an area where an intermediate tailings product was dumped, so it was not used for the current tests. I've also included a breakdown of copper concentrations, and it tells a bit of a different story, with 2019 values below the average of the 2012, 2018, and 2020 values. But one of the interesting things was that even though the 2020 sample had average tungsten and copper concentrations, the iron and sulfur concentrations were much higher than the 2019 sample. The 2012 samples show a much greater range in iron concentrations compared to the range for tungsten, and that range does reach the values of the 2019 and 2020 samples, but the 2019 and 2020 values remain at the upper edge of that range. And here you can see that the range in sulfur values for the 2012 sample do not even reach the values of the 2019 and 2020 samples. These results show that there is a greater range in element contents than previously expected, which influences the results of the oxidation and flotation experiments. Mineralogy of the initial samples was investigated before any testing occurred to establish a baseline. Modal mineralogy by SEM with automated mineralogy shows the 2020 sample is dominated by pyrrhotite and iron oxides. Dolomite and calcite are present, but at substantially lesser quantities than pyrrhotite. Scheelite is also present in all of the tailing samples. The pyrrhotite grains in the initial 2020 sample show varying degrees of oxidation, which is evident from these backscatter electron images. Here I'm showing examples of unoxidized pyrrhotite, pyrrhotite that has been rimmed with iron oxide, and then moving to pyrrhotite grains that have been substantially oxidized until almost all of the pyrrhotite has been replaced with iron oxide. The next characterization piece was particle size distribution. The P80 was determined to be 212 microns, which is expected for tailings from a flotation circuit. Standard Proctor tests were performed on the 2020 sample to determine the optimum water content, and that was at 16%, corresponding to a maximum dry density of just under 1.91 grams per centimeter cubed. Moving into the sulfide oxidation column experiments, water content was monitored continuously by the TDR probe in the middle of the column. Since the columns were left open to the atmosphere, the water content decreased over time due to evaporation. Each of the red bars on these figures indicate the time when an oxygen consumption test was occurring. During the time the oxygen cap is on, the change in the volume percent of oxygen in the headspace is monitored, which corresponds to sulfide oxidation, as it is an oxygen-consuming reaction. From these three graphs, it is evident that the first week, shown in blue, resulted in the most substantial decrease in oxygen. But what was unexpected was that the most unsaturated column, column 2, shows the least oxygen consumption overall, potentially indicating that oxidation reactions are not occurring to the same extent as they are in the wetter columns. The oxygen consumption slows dramatically after the first test, which may be caused by passivation of pyrrhotite. Looking more closely at the first hour of oxygen consumption can indicate the initial sulfide oxidation rate. Column 2 shows the highest rate of decrease in the first test, but a much lower rate for every test following. In column 2, the rates have only declined as time has progressed, but in columns 1 and 3, the rates have increased for a week or period of weeks and then decreased again. For all the columns, pH has remained around neutral, and surface temperature has followed the air temperature. For my first objective of characterization, the main findings include the variable geochemical composition of the tailings with high iron and sulfur contents, the high pyrrhotite contents with varying degrees of oxidation, and the optimum water content is 16%. For my second objective of evaluating sulfide oxidation, I've established that sulfide oxidation is occurring, but is currently buffered by the carbonate minerals present in the tailings. I've also determined that the rate of oxygen consumption varies with water content, and the oxygen consumption substantially decreases after the first exposure. In the future, the focus will be on the second and third objectives. The goals will be to evaluate any changes in sulfide oxidation caused by different compositions of tailings, and looking into what impacts the oxidation could have on the quality of the water from the filtered tailings and what the scales of those risks are. For Objective 1, the next step is to characterize post-test samples from the columns to compare mineralogical changes from the initial samples. Objective 2 will involve starting a second and third series of oxygen consumption tests, focusing on how oxidation is impacted by maintaining constant water content and by changing the composition of the tailings. Reprocessing experiments are being conducted at the Queen's Mining Department, and tailings from those tests will be used for this third series. Objective 3 will involve conducting oxygen consumption and water quality tests on site to assess the potential for environmental harm to occur. Thank you so much for your attention. I appreciate you taking the time to listen to this presentation.